Welcome to the first video about the basics of graphing polynomial functions. So let's just do kind of a quick little overview of what the graphs of polynomial functions look like. So you've got a table here, and in the top row of the table, we're going to look at the graph of polynomial functions of varying degrees, of increasing degrees, that have a positive leading coefficient. So y equals x. Okay, that is just a line. It starts in the bottom left, goes to the top right, has a slope of 1. If y equals x squared, that is a quadratic. It's a parabola. Notice something here. Notice that we go top left, bottom right on x, y equals x. We go both sides go up for x squared. Okay, x cubed. Oh, I accidentally clicked it twice, but that's okay. X cubed starts in the bottom left and goes to the top right in exactly the same way that y equals x does. Okay, and then x to the fourth, this quartic, this fourth degree polynomial, has a similar end behavior. The behaviors of the ends of the graph does a very similar thing to what y equals x squared does. Okay, now in the bottom row we have the same functions here, the same graphs, except we're multiplying everything by -1. Okay, so we know from transformations that that's just a vertical flip, right? But leading coefficient here, the coefficient in front of the first term, the highest degree term, is now negative. And consequently, we have the opposite happening with the end behavior, whereas with y equals x, we started with the bottom left and went to the top right. Now we are starting in the top left and going to the bottom right. It follows that y equals negative x squared, where both sides would go down. Okay, y equals negative x cubed. It's the opposite of y equals x cubed. So instead of bottom left to top right, now it's top left to bottom right. And then finally, the negative version of the fourth degree polynomial, both sides go down. From looking at this graph, a few things are clear. First of all, if we have a polynomial of even degree, so fourth degree polynomials, the end behavior is the same. So on the left side of the graph, it is the same as the right side of the graph. It goes up, they both go up, or they both go down. Okay, so that is true for every even degree polynomial. And you can see here the same thing for x to the fourth. Both go up or both go down. For odd degree polynomials, okay, odd degree, first and third, and this to be the same for fifth and seventh, the ends do the opposite thing. So we have bottom left, top right. We have top left, bottom right. They go in the opposite directions. And that will happen for every odd degree polynomial. And the final thing that we know is that and if we have positive leading coefficients, we emulate like a slope of a line that's like a positive slope of a line. So it's always going to go bottom left, top right, or these things both point up. It's natural to think if we have positive, both things go up, because up is associated with positive. Okay, and if we have a negative leading coefficient for an odd degree polynomial, it's going to do what a line of a negative with a negative slope would do. So it starts at bottom left, goes top right. Okay, bottom left, top right. And then just like with positive leading coefficients, we go up and up. For negative leading coefficients on even degree polynomials, we go down and down. Down associated with negative. All right, here's a summary of what we just said. So for an odd degree polynomial with a positive leading coefficient, we're going to expect to have end behavior that does something like this. Okay, it's going to start in the bottom left, goes to the top right. For an even degree polynomial with a positive leading coefficient, it's going to start in the top. It's going to go up and up, like both ends are going to go up. And then for a odd degree polynomial with a negative leading coefficient, meaning the coefficient in front of the highest degree term is negative, it's going to start bottom left, go top right. It's going to kind of follow like a line with a slope, a negative slope. Okay, and then for a even degree polynomial with a negative leading coefficient, we will have something that does this. Okay, we're going to have it going down both directions. Now, this terminology we're using here, where like they both go up, or we go top left, bottom right, that's not what we use in math. There's actually a kind of standard way to talk about end behavior, and that's called limit notation. Okay, limit notation is something we use a lot in calculus, and it's kind of fundamental to the subject of calculus in a lot of ways. And it's really something that's very simple. It shouldn't be intimidating at all. Let's say I have a function, so f of x, right? And I wanted to know specifically, like what happens at a certain place on that function. Well, it's instead of just saying, all right, let's say that value there is like c, that x value is c, then this would be f of c right here, right? Instead of saying, all right, we just plug in c and we get what it is, which we totally can do. What limit notation is it's examining what's happening when we're plugging in values for x that are really, really close to c. So we're getting really, really close to c on either side. When I say really close, I mean infinitesimally close to c, like basically c, but not quite. Like if c was 1, we'd be plugging in 0.9999999. Okay, what would f of x be? What would f of 0.99999 be, right? And then same deal, we can look at it from the other direction too. And so limit notation basically is this. And the way it's written is limit, so lim, that's short for limit, as x approaches some value, and we'll call that value c, of the function, so in this case the function is f of x, is equal to some number, some value, and that value is like L. Okay, now uh, we're not going to talk about limit notation as far as where it is, like how do you evaluate at a certain point? How do you find a limit at a very certain point? When we're in this class, when we talk about limit notation, we're going to focus on using it in the context of end behavior. Okay, so if I want to use limit notation to describe end behavior, I'm going to be plugging in values for x that are really, really, really big. What's happening at the very end of this graph on either side? Like, so really big negative x values or really big positive x values. And you can think of it like this. The limit as x approaches like really big positive values, so as x approaches infinity, not infinity, just before infinity. What's happening to f of x at that stage? And we can look at, there's a couple of ways we can think of this. First of all, we can just look at the graph and say, okay, as we're plugging in really big x values, this is just going to keep going down forever. So the limit of f of x as x approaches infinity is negative infinity. It would be going down forever. Another way of saying this, because something can't ever equal negative infinity, we can say that the limit as x approaches infinity of f of x does not exist. Okay, maybe you don't say equals dne, just say does not exist dne. Okay, that's two different ways to say the same thing. Okay, we can also say, because if we look at the other side of the graph, right, as we're plugging in really big negative x values, and if we're plugging really big negative x values, you can see that we just keep going down forever here. That the limit as x approaches negative infinity now of f of x, sorry, you write f of x kind of in line with the limit. I just sort of am not good at writing on this tablet. Limit as x approaches negative infinity of f of x is also negative infinity. Okay, and again, you could say the same thing here, right? The limit as x approaches negative infinity of f of x does not exist either, right? It can't be equal to infinity. Okay, and now note that will be the same for every even degree polynomial that has a negative leading coefficient. And so we don't actually have to look at the graph. If we see that it has a negative leading coefficient and it's an even degree polynomial, this is the end behavior of that polynomial. Okay, now we can look at this next problem here. We have a positive leading coefficient, odd degree polynomial. The highest term is odd, has an odd exponent. And so what that means is we're going to be going, top left, we're going to be going bottom left, top right, right? So when we plug in really big negative x values, we will have very big negative y values, right? F of negative infinity is going to basically be negative infinity. So we can write this as the limit as x approaches negative infinity for g of, I said g and I wrote f. G of x is going to be negative infinity. And the limit as x approaches positive infinity of g of x is going to equal positive infinity. And this will be the case for every odd degree polynomial with a positive leading coefficient. These here would be opposite if we had, a negative leading coefficient. And so that's limit notation.